Welcome to Statics Week 4 Monday lecture. We'll work 3 problems out of particle equilibrium today. And on Wednesday, we'll look at a 3D problem in particle equilibrium. And if we have time, we'll start on chapter 4. Well, here's the first problem we want to take a look at. This is a diagram of it's a cable system. Attached here, there's a vertical cable attached today that's lifting this load of 900 pounds. 2 lift cables, AB and AC, are attached at an angle theta to the 900-pound load. And conditions are that AB and AC have a maximum capacity of 800 pounds. That being the case, we want to find the smallest theta, which AB and AC can be attached to the load of 900 pounds. So the first thing we do is draw a free body diagram. And what we do on the free body diagram is separate the structure from, in this case, the 3 cables. And we see the cables are acting at a point A, so we have a particle problem. And the free body diagram would look like this. Okay, here is point A. The 900 pounds, since this system is lifting 900 pounds, this cable here has to have the 900 pounds carrying it up. Okay, so this 900 pounds is going to be transferred to this cable lifting. If it was 1,000 pounds, it'd be 1,000 pounds in this cable, vertical cable at A. So this is 900 pounds. The cables that attached AB and AC have a maximum capacity of 800 pounds. So we draw those with 800 pounds each. 800 pounds each. And very simply, all we have to do is some forces in the y direction equal to 0. And we have the 900 pound directed upwards. And both of these are the same, both 800 pounds, the angle's the same. So we'll just have 2 times, and its vertical component, this is theta, the opposite theta, so that's the sine function. So 2 times 800 sine theta equal to 0. And so what we have then is 900 minus, taking this, 2 times 800 is 1,600. So 900 minus 1,600 sine theta equals 0. I'll rewrite this. 900 is equal to 1,600 times sine theta. Sine theta then is equal to 900 divided by 1,600, 0.5625. Theta then is equal to 34.2. So theta is equal to 34.2 degrees. Pretty straightforward. I think the key here is recognizing that if this total load is 900 pounds, it has to be 900 pounds in this vertical cable lifting. And again, theta here, if we draw a horizontal line here, theta is this angle. Same thing up here. This is theta, which is what we have here in our free body diagram. Okay. That's the first problem. So the second problem is a two-wire or two-cord cable system. It could be, let's call them cords, two-cord system. One cord is working around a pulley system here, and then another cord is attached where the pulley is attached off at some angle theta. Okay. There is a cable limit, a cord limit of 100 pounds. So there's 100 pounds max in this system here around the pulley system, and there's 100-pound max in this single cable up here, DB. And what we want to know is the value for W. And this angle theta that we have DB acting at. Okay. We do have a slope given for this part of the cable system. It's 5 horizontal, 12 vertical, and so it's 5, 12, 13. 13 would be the hypotenuse. Two equations have two unknowns, angle theta and W. So we need to utilize the two equations. So I'm going to sum forces in the X equal to 0. This has an X component. This link over here has an X component. And using slopes, this is in the X direction. This would be 5/13 of W. That's positive. This 100 pounds has an X, and this is going to be in the negative X direction. It'll be a cosine function. Okay, it's adjacent. Okay, it's adjacent in the X direction. And it's minus, so this is minus 100 cosine theta. Give us this component in the X direction. And you can write this out. 100 cosine theta then is equal to 5/13 W. So I just wrote it out that way. Some forces in the Y direction. Okay, for some forces in the Y direction. We have three components. We have this vertical Y. We have the Y component on this side of the cable. And of course, we'll have a Y component on the top side over here. Okay, on the DB cable. So let's take this one first. It's in the positive Y direction, so it's 100. And again, the vertical component is going to be, here's the angle theta, is going to be opposite, so it's a sine function. Okay, so it's 100 sine theta. And we have a minus W here. And using slopes, 12/13, okay, 12/13 W minus 12/13 W equal to 0. So we have sum of forces in the X and sum of forces in the Y. I'm going to rewrite these then. We have these two equations, some forces in the X and some forces in the Y. I'm going to write this equation here like I did 100 cosine theta. And we have 100 sine theta. W is would be 13/13, so it'd be 25/13 W. Okay, so I have 100 sine theta, well, 25/13 W. I think if you sort of recognize something here, we have sine and cosine. So what I'm going to do is just write these a little bit differently, put them together. So what I have here then is 100 sine theta is equal to 25/13 W. Right below this, I'm going to write the other equation, 100 cosine theta is equal to 5/13 W. Now remember, we have two unknowns. The angle theta and then the weight. I don't know what the weight was also. So we got theta and weight. You could use substitution. I don't know why that would be messy, but what if I do this? Make a math problem out of that. What if I put a division sign here? So I have sine theta divided by cosine theta. Hundreds are out. So sine theta divided by cosine theta. And I got 25/13 divided by 5/13. 13's out. 25 divided by 5 equals 5. And I'm left with W. W's cancel out too. So in effect, what I have is sine theta over cosine theta is equal to 5. Well, that's a tangent function. The tangent theta equals to 5. Theta then equals 78.7 degrees. I've got theta. I can plug back into either one of these equations up here, and I can solve for W. And W is equal to 21 pounds. Let's see, didn't matter which one we use. I just use this equation down here. They both, you can check both of them and come out. So if I could go 100 cosine of the angle was 78.7 degrees equals 5/13 W. We got everything in here to solve for W, and W then comes out to be 51.0 pounds. Which is okay, because if we go back to look at our system here, the max is 100 pounds anywhere. We assumed it's going to reach up here, but so this is okay. W, it doesn't exceed 100 pounds. Okay, so it's less than 100 pounds. And we're good on that one. Third problem is a spring problem. So we have a situation, we have basically three forces acting in this system. Suppose we have some wire or cable, maybe probably something up here. Doesn't matter what the material is at this particular point. They're all attached at this point B. Here's the spring. And we have these two members, BD and BC, attached to some wall system, some support system over here. We're given dimensions. This dimension is 400 millimeters. This is 300 millimeters this way for this dimension. And it's 400 millimeters across here. This is the stretched length of the spring. And what we want to know is the force in BC and BD when the spring is in this position. Okay, so it's stretched, so there's going to be a force in AB, and we're going to be able to determine exactly what that force is. Okay, what we do know is that the unstretched length of the spring is 200 millimeters. And in this situation with a force applied, we know it's 500 millimeters. So what we do know is that the stretched length is going to be 300 millimeters. Okay, so we know the stretch length of that system is going to be 300 millimeters. So the stretch length of the spring equals S. It's been stretched to 500. The unstretched length is 200. So S then is equal to 300 millimeters. Okay. So now what I need to do is draw my free body diagram. And again, the way I'm going to approach this is remove all the supports. So I'm going to remove this wall system, this wall system over here, or support whatever we have. And all three forces are acting at a point, so I have a particle problem. So my free body diagram is going to look. This is BC. This is BD. And this will be the force in the spring. And what I need to know is the K value, which is the spring constant. So this K value is 800 newtons per meter. And we know the force in the spring is equal to K times S. Newton meters, note that. So force in the spring is equal to K, 800 newtons per meter. Now, what's and S is going to be the stretch length. The stretch length was 300 millimeters. And this is the first place that you could make a mistake. K, the units are Newton meters. We have millimeters, so we need to make sure that our S is in meters. So 300 millimeters is 3/10 of a meter. So it's 3/10 of a meter. So 3 times 800 is going to be 240 newtons. So the force in the spring then is going to be 3 times 8, 240 newtons. What else do I need to get some angles on here. Angles or slopes. I want to use an angle on this one. So if we've got distances, so this is 400 vertical, horizontal is also 400. So it's basically 400 this way and 400 this way. It's 45-degree angle. And it's going to be easier to use slopes on this one than an angle, be less bothersome to do it this way. This one is 300 vertical, 400 horizontal, 3, 4, 5. Okay, so the slope on this is a 3, 4, 5 slope. Three vertical, 4 horizontal, and 5. So it's a 3, 4, 5 slope. So it looks like we have everything we need to have to go ahead and solve the problem. And I'm going to do my references back and forth. Using this, we'll go back. So I'm going to do equations of equilibrium. So I'm going to sum forces in the x direction equal to 0. I have to keep going back and forth here. And keep in mind what we have in our free body diagram here. Okay, we have this X component, which is the spring force, 240. We're going to have this X component of BC, which is going to be BC, and again, it's adjacent, so it'll be cosine of 45 degrees. And for BD, it's going to be positive x2, and using the slopes, it's 4 horizontal, 5 hypotenuse, so it's 4/5 of BD when we do that. So I'm going to write my equation, and the spring is going to be negative when we do this. So I have force in BC cosine of 45 degrees plus 4/5 force in BD, and then the spring was a negative direction, so that's minus 240 equal to 0. So it's 0.707 force in BC plus 0.8 force in BD equals 240. I have two equations and two unknowns, so I'm going to get this. So here's my equation 1 that I'm looking at. Some forces in the y direction equal to 0. I only have two forces in the y direction. Okay, so we're looking at this. The y component for BD using slopes will be 3/5 BD. And the y component of BC, it's opposite, it'll be sine of 45, sine and cosine, same value, but we're using the proper notation. It's opposite that, so it'll be sine function, sine of 45 degrees. Okay, so we have two components in the force of the y direction. So we have force BC sine of 45 degrees. And then we said BD. And we're in the y direction, so BC is positive. Okay, here's our free body diagram. BD is going to be negative. Keep track of our signs. The y component for BD is negative, and it's going to be 3/5 of BD. So minus force in BD, 3/5 of that, and that's equal to 0. Rearrange this a little bit. Force in BC sine of 45 is 0.707. Equals 6/10 force in BD. This is equation 2. So I end up with two very simple equations now, and just substitute. And I substituted 2 into 1. I substitute equation 2 into 1. Okay, so for however you wanted to do that, you can go ahead and just substitute back in here. Okay. Either using FC or BD, either one, back into this one. So just a substitution works. And then you go back the other way to solve for the other one. And when I did this, I end up with a force in BC is equal to 145 newtons. Force in BD then is equal to 171 newtons. Like I said, you could do your substitutions any way you wanted to do your substitutions. Okay. That's the spring problem. Those are 3 problems I wanted to work for you. And the Wednesday lecture is going to focus on a 3D problem. And if we have time, we'll get started on the next chapter, chapter 4. So I will see you in a couple of days again on video.